Hello folks, this is the second video on the kinetic theory of gases, and in this video we're going to talk about gases made up of molecules which are diatomic and molecules which are polyatomic, and we're also going to talk about the equipartition theorem. Alright, so we're going to start with a very strange example. This is a container and a gas of diatomic molecules. Now each of these molecules is represented by 2 point particles connected by essentially a spring. Now obviously a real life diatomic molecule is not like that. It is governed by quantum mechanics. But this is a simple classical model that we are building, and these models form the basis of the kinetic theory of gases. Now with these simple models, we are actually able to predict a large number of the properties of gases. Alright, so imagine that all these molecules are aligned in the same way and they're all moving to the left in some uniform fashion. What happens when the molecules collide against the left wall? They bounce back. When they bounce back, you're going to have one of these molecules moving in this direction, colliding with another molecule which is coming in this direction. What happens when these two collide? When these two collide, this molecule will start spinning in that direction and this molecule will start spinning in that direction. So pretty soon after these collisions, many of these molecules are spinning even though they were not rotating initially. Now, let's say one of these molecules, which is spinning like this, let's say it comes and hits another molecule which is still going in that direction. What happens when this comes and hits this? Then this molecule will start vibrating. What does that mean? That means the bond length starts changing. So pretty soon through all these collisions, what was initially entirely translational kinetic energy has now been redistributed into rotation as well as vibration. So pretty soon all the molecules are translating. That means the center of mass has a velocity. They are rotating about the center of mass and they are also vibrating. So all the energy that we initially had in the gas has now gotten redistributed into translation, rotation, and vibration. So we have a question. If a gas has a total internal energy of U, how much of that is in translation, how much of that is in rotation, and how much of that is in vibration? Alternately, let me rephrase the question. Supposing I have a gas, I supply it with some heat. How much of the heat goes into increasing the translational kinetic energy? How much of it goes into increasing the rotational kinetic energy? And how much of it goes into vibration? This question is answered by the equipartition theorem. Now, in every course that you have taken, your teacher has told you about degrees of freedom. So I'm going to explain degrees of freedom now, but it's very important to understand that a very clear understanding of this is not really essential for what follows. Still, let's go ahead and try to understand degrees of freedom. Degrees of freedom of a molecule is essentially the number of coordinates that I need to describe the configuration of the molecule. What does that mean? So, if I take a monatomic gas, if I consider one of the molecules, which is an atom, and I'm going to treat it as a point particle in the kinetic theory of gases, now how many numbers do I need to describe its position? I need 3 numbers. So, we call it 3 translational degrees of freedom. That is, I need x coordinate, y coordinate, and z coordinate, for example, to locate the particle. What if it's a diatomic molecule? If it's a diatomic molecule, there are 2 atoms. So I am going to need, so this is monatomic. What about a diatomic molecule? A diatomic molecule has got 2 atoms, and a complete description of the configuration of the molecule requires 6 numbers, 3 coordinates for one atom, 3 coordinates for the other atom, 6 degrees of freedom. And if I take a polyatomic, for example, specifically I'm going to take methane. If I take methane, you have carbon and 4 hydrogens in a 3-dimensional structure, and essentially how many numbers do I need? I need 1, 2, 3, 4, 5 atoms. 5 atoms are described by 5 times 3, 15 coordinates. Now, It turns out that this is not how we describe molecules. There is a different description of the molecule that we can give, which is locate the center of mass of the molecule. That requires 3 coordinates. As far as the monatomic gas is concerned, that's these 3 numbers. Done. When it comes to a diatomic molecule, instead of describing the configuration of this molecule by giving x1, y1, z1 and x2, y2, z2, let's do a different thing. Instead of that, we are going to give the coordinates of the center of mass, that is 3 numbers, x coordinate of the center of mass, y coordinate of the center of mass, z coordinate of the center of mass, plus the orientation of this molecule. How do we describe the orientation of this molecule? Think of it like this. Let's place the molecule here. This is the center of mass and these are the 2 atoms. Now watch this. I'm going to draw a sphere centered at the center of mass, and if I locate this point on the surface of the sphere, that gives me the complete description of the orientation of the molecule. To locate this point on the surface of the sphere, I need 2 numbers, latitude and longitude. So as far as rotational degrees of freedom are concerned, we have 2 more numbers. Once this atom is located, diametrically opposite is the position of the other atom. Now we are forgetting one important thing. What about the bond length? The bond length can change during vibration. So that means the configuration of the molecule may not be this, but at some instant of time it may be that. So I need 1 more number to give me the bond length. Plus 1. So it's going to be 3 plus 2 plus 1, 6 degrees of freedom. But instead of describing the molecule in terms of the position coordinates of the 2 atoms, we describe it as the position of the center of mass, the rotational orientation, and this is the vibrational degree of freedom. Okay? So in this way, with a polyatomic molecule, for example, even a simple one like water, you can see the vibration can consist of change of the bond angle. It can vibrate like this. It can also vibrate where the bond lengths are changing. So there are many ways in which it can vibrate. But I can describe it in terms of, again, 3 translational degrees of freedom for the center of mass, plus I need 3 rotational degrees of freedom. Why do I need 3 rotational degrees of freedom? So let's take a water molecule, for example. The center of mass is out here. As before, I am going to draw a sphere centered at the center of mass. Now, as far as the orientation of this water molecule is concerned, one way to do it is I may pick the line from the center of mass through the oxygen atom, and where it falls on the surface of the sphere, that gives me a certain orientation of the molecule. That means I need 2 numbers for this. But notice one important thing, it can also rotate about this axis. So there is 2 plus 1, so there are 3 rotational degrees of freedom. And then several vibrational degrees of freedom, and the total will amount to 15. Now, how to find these vibrational degrees of freedom? You will see that we don't need to in this course. So let me summarize. As far as degrees of freedom are concerned, for a monatomic gas, each molecule, I need only 3 numbers to locate its position. For a diatomic gas, for each molecule, I need 6 numbers, 3 translation, 2 rotation, and 1 vibration. And for a polyatomic gas, again I need 3 translation, 3 rotation, and several vibrational degrees of freedom. Now, do I need to understand all this clearly? Not really. Let me take you to the next step. Now that you have an idea of what degrees of freedom means, we are ready to state the equipartition theorem. But before I do that, let me point out something very important, which is when you take a gas, different molecules are moving with different speeds. They are moving in different directions. They are vibrating with different amounts of energies. They are rotating about different axes with different amounts of energies. Can we say something about the average energy in rotation, in vibration, and in translation. The equipartition theorem tells us that on average, per molecule, the amount of energy there is per degree of freedom is half kT. How do you apply that? Let's take translation. Whether it's a monatomic gas or a diatomic gas or a polyatomic gas, the number of degrees of translational freedom are 3. Which means, on average, each molecule has got an amount of kinetic energy equal to 3 by 2 kT. Half kT per degree, 3 degrees of freedom, so 3 by 2 kT. Now you can apply this even to DNA molecules which might be floating in the air, or to a smoke particle or a dust particle. Now, let's look at rotation. Diatomic molecules have got 2 rotational degrees of freedom. So therefore, on average, they have 2 times half kT, that is, kT is the amount of energy per molecule in rotation. Now, as far as vibration is concerned, there is a twist in the story. Per vibrational degree of freedom, we do not give half kT but kT. Now, there is a reason for this. But for the moment, let me put the reason aside. Let's learn the number of degrees of freedom. So let's make a table. So whether it's a monatomic gas or a diatomic gas or a polyatomic gas, there are 3 translational degrees of freedom because there are 3 numbers I require to locate the position of the center of mass. So we have 3 translation for monatomic, diatomic, and polyatomic gases. Monatomic gases have no rotational degrees of freedom and no vibrational degrees of freedom. So the average, I should write average energy per molecule is going to be 3 times half kT. So 3 by 2 kT is the amount of energy per molecule on average. Now for diatomic gases, we have 2 rotational degrees of freedom and 1 vibrational degree of freedom. It can vibrate like this. Now, let's ignore vibration for now. I'll tell you why. If I ignore vibration for now, I get 3 plus 2, 5. So 5 times half kT, it is 5 by 2 kT, is the amount of kinetic energy there is in translation plus rotation per molecule of, let's say, oxygen or nitrogen or hydrogen. For polyatomic gases, like ammonia or methane or even steam, water gas, we have 3 translation degrees of freedom and 3 rotational degrees of freedom and several vibrational degrees of freedom, which we are going to ignore. If I ignore vibration, we have 3 plus 3, 6. 6 by 2 kT is the average energy. Now, let's keep ignoring vibration. I'll explain why. Let's now calculate the total energy per mole. So now, monatomic gases, we have 3 by 2 kT per molecule. So if I multiply it by Avogadro number, K times Avogadro number is going to be, that is Boltzmann's constant multiplied by Avogadro number, gives me R, the universal gas constant. So the internal energy per mole, N is equal to 1, is going to be 3 by 2 RT. Now N is 1. If I look at this equation and compare these two, we find CV is 3 by 2 R. So from the kinetic theory, we're actually able to predict what the molar specific heat at constant volume should be. Interestingly, all monatomic gases, whether it's helium or argon, they're all going to have a CV of 3 by 2 R as long as they behave ideally, which means at high temperatures, low densities. If CV is 3 by 2 R, Cp is Cv plus R, so that's going to be 5 by 2 R, and gamma is Cp by Cv, which is going to be 5 by 3. This is the gamma that you use in PV to the power of gamma in describing any adiabatic process. Let's look at diatomic gases. Diatomic gases, totally ignoring vibration, we have 5 by 2 kT per molecule. So per mole, it's going to be 5 by 2 RT. If you have n moles, it's going to be multiplied by n. Here also, if you have n moles, it's going to be multiplied by n. If I compare these two expressions, you get immediately that for diatomic molecules like oxygen and nitrogen, the CV is 5 by 2 R, Cp is 7 by 2 R, and gamma is 7 by 5. And lastly, for polyatomic gases like methane and ammonia, you have, ignoring vibration again, 6 by 2 or 3 RT for n moles multiplied by n. So CV, comparing these expressions, is going to be 3R, Cp is 4R, and gamma is 4 by 3. Now, why did we ignore vibration? We ignored vibration because when we went to the laboratory, when I say we, not me, I'm talking about scientists, when they went into the laboratory and measured CV and Cp and all, they found that the observational values agreed with these values, with these numbers, which you got by ignoring vibration. When you include vibration, for example, a diatomic gas is 1 degree of freedom vibration. If it's 1 degree of freedom vibration, you have to add plus per degree of vibration, not half kT, but kT. So I should add RT per mole. Let me remove n here. So we are talking about per mole. So this becomes 5 by 2 plus 1, 7 by 2. So this becomes 7 by 2 R, and this becomes 9 by 2 R. And experimentally we find that the answer is 7 by 5, not 9 by 7, as predicted by the kinetic theory of gases. In other words, we are finding that nature for some reason is ignoring vibration. That is, when a certain amount of heat is supplied to a gas, the energy, the heat energy, seems to go into translation and rotation, but doesn't seem to go into the vibrational degrees of freedom. Now, this was a mystery until quantum mechanics came along. Now, the quantum theory predicts that energy levels are not continuous, but they are quantized. The vibrational energy levels are so widely spaced that at ordinary temperatures, the collisions between the molecules are not strong enough to excite the molecules to higher vibrational levels. They stay in the ground state. If you raise the temperature of the gas to more than around 1500 Kelvin, then you find that the collisions are strong enough to excite vibration, and we find that the prediction of the kinetic theory of gases, which is CV equal to 7 by 2R, Cp is equal to 9 by 2R, etc. for diatomic molecules, turns out to agree with experiment. But at ordinary temperatures, vibration is completely ignored. That's because of quantization. Now you might ask the question, what about rotation? Are the energy levels of rotation not quantized? The answer is yes, they are quantized too. But the quantum mechanics predicts that these energy levels are so close together that at ordinary temperatures, collisions are strong enough to excite rotational energy levels. So when I supply heat, the heat goes into rotation also, apart from translation. Naturally, you will ask, what if I cool the gas down? At sufficiently low temperatures, the collisions are now not strong enough to excite rotation. Then what do you have? Then you find that the rotational energy levels also should be ignored at low temperatures. You find that CV for a diatomic gas is just not 5 by 2R, but just 3 by 2R. And same for polyatomic gases. So finally, the answer to this riddle came from quantum mechanics. Alright, so we're going to stop this video here, and in the next video, we're going to solve some problems. So goodbye for now. See you in the next video.